Our first speaker is going to be Phil Tully, talking about ranking relevant malware strings using weak supervision. Let's see. Phil received his joint PhD from the University of Edinburgh and the Royal Institute of Technology. He is currently a staff data scientist at FireEye, working on categorizing malware and social media disinformation.
Great, thank you. Thanks, guys. All right, so just a few bookkeeping things at first. This was a project that was a collaboration internally at FireEye between the FireEye Labs reverse engineering team. I'm going to talk to you about how we can take the domain knowledge of those reverse engineers and inject it directly into our models. That's going to kind of how I'm going to argue how we use weak supervision today to solve this problem. And then also the data science team, which I'm a member of. There's a bunch of us here. We're hiring data scientists across the experience spectrum. So if you're interested in this talk or any other talks, please come find me or anyone else on the team afterwards. We'll be happy to kind of talk to you about that. So we built a tool that takes strings and ranks them according to their relevance for malware analysis. And so to motivate that, I want to start off and take a step back and try to justify and define what a string is in the first place. Why do we care about these things when it pertains to malware? Strings are assets for malware analysts. So they persist throughout compilation, right? So if we have a very simple C program here that prints the strings 1337 and then just returns, that's going to be compiled and assembled into an object file where it's going to exist unless it's been dynamically generated, but generally it will exist. And then eventually in the executable, which is what the reverse engineer will see, it will exist somewhere in that file. Here in this contrived example, it exists in the data section, but in theory it could kind of end up anywhere within this binary. And so this is an asset that we can use. The reverse engineer's job is to take that string and try to figure out how we got, what source code created this string in the binary, right? That's kind of like a very simplified version of what they're doing. But anyway, this is something that we can use as malware analysts and try to make conclusions about what the purpose of this thing was. Strings can be either ASCII or narrow strings. So typically they're just printable characters within the executable. So there are n of these bytes in a row, and typically is 3 or 4 followed by a null byte. And the problem is with this is that there's no formatting or context that's used to print these characters out to the file. So strings can end up showing up as random jumbled things. You can say things like, well, this simple program, the intention was to print 1337, right? But if you're looking at the strings output of an executable, it's not always going to be the case. So it can be things like memory addresses or x86 random junk instructions that show up, or some other data that's used by the program that's not really relevant for the job at hand, which is trying to understand what this malware is doing. And so not only ASCII strings, but Unicode strings and wide strings. And so typically when you run strings in a file, you want to capture both of these types of strings because, especially for PE files, the signal-to-noise ratio for Unicode strings is going to be typically much higher. And so the difference here is just that Unicode strings are 2 bytes in length and they're double null terminated. So now we know what that is. This is what the canonical strings program is doing. You just have an input file and you run this program over it and it produces a bunch of strings for you. And so here in this example, you have an assortment of different strings, right? So you have things like program names, you have path names, you have user agent strings, you have format specifications, and you have things that look like function handles and function names, but you also have some junk in there and you have some PE header artifacts and things like that. So the job is for the reverse engineer and malware analyst to try to take this story of what these strings are showing and come to some conclusions. But the caveat here is that you can't make conclusions just based on strings, right? This is only one part of the static analysis pipeline and process for the malware analyst, right? So you would never want to say, this string exists in the file, therefore it is or it is not malware, right? So that's a caveat here. We don't want to make any claims about detection, right? This is kind of more upstream than that. So how does this work at FireEye and what I guess elsewhere, other companies are doing this too. But a customer or a soon-to-be customer will suspect a compromise. And so there's a piece of malware sitting on one of their endpoints or machines. And at that point, the IT team is probably going to try to understand what it's doing, And to do that, they're going to do things like strings, right? They'll execute it at that level. If it gets escalated to the level of incident response, so you have people actually go on site and do some more forensic analysis on the malware, they're going to run strings again, right? So this is something that's done kind of ubiquitously across the spectrum. And then if the response handlers can't figure it out, it's a very complicated piece of malware, eventually gets escalated up to the reverse engineer level, and it'll get triaged by malware analysts who, again, will run strings. It's a very interesting and easy to do part of this pipeline that will give you some valuable nuggets of gold about what the malware is capable of. Again, caveat, sometimes, not all the time. And so not only these kind of personas, but SOC analysts run strings, red teamers run strings, malware researchers. We've seen different PE file detection work done here where strings are features, so they're relevant for these. And someone like me, who's a malware analyst noob, will run strings on a piece of malware to try to get a general idea of what it's doing. And like I said, experts will run it just as well. So it's kind of ubiquitous across the malware analysis spectrum here. Now in practice, and as I go through the slide, you'll see on the right-hand side what this looks like. This is what the malware analyst will see when it runs strings. It'll have to scroll through a long file like this and try to pick out the interesting ones. So you'll see a bunch of junk here. This is kind of motivating the problem for us. Running it on larger binaries will produce tens of thousands of strings, but most of that stuff generally is going to be junk. And so what we want to do is just take a hypothetical broom and sweep all the interesting stuff up to the top, right? We want to just focus on the stuff that's interesting here, and push all those kind of junky strings that you're seeing along the right-hand side, just push them down to the bottom. Now, typically, knowing which ones are relevant often requires highly experienced analysts, so we have a labeling problem here. This is not something that I could do off the bat, for example. And significance is kind of subjective, and so different malware analysts might disagree on which strings are relevant or not, and different roles across that might disagree. So what we wanted to do was kind of build a tool that would kind of unite these different goals and try to tackle them differently. But what we wanted to do is just build this simple tool, easy to use, that would efficiently identify and prioritize the strings for the malware analyst so that they can have this effect of the sweeped strings being pushed towards the top. And we want to have it obviously based on the relevance for malware analysis. And we want to make it very easy to use so that it's portable, and that it generalizes across different personas in the InfoSec world, and that it can be used for downstream applications. And of course, the whole goal here is to save time and to save money. And so how does it work? We're going to frame this as the learning to rank problem. So the whole idea here is we want to create an optimal ordering of a list of items, a different permutation of a given list of items, and return that to the user. And so the difference here compared to your typical classification or clustering task is that you're making predictions on single items, but you're making them with respect to other items in that list. And so the eventual score is not concerned about a single binary or a single piece, a single string, but it's actually how those strings are ranked with respect to each other. So you have this notion of relevance and respect to each other. And so it's fundamentally different, and from what I've seen at least, this is kind of rarely applied in security applications, maybe for some recommendations of alerts and things like that, but I kind of want to push this out for you guys as a way to think about your problems in a different way as well. And so to kind of formally drive this a little bit more, how do we pose this as a supervised learning task? And as you see, we have the input files, we run strings over them, and we can produce a bunch of potential training data for us. And so here you have each individual rounded circle there representing a single string's output, and each string's output contains a list of strings. And each of those strings is going to be associated with an ordinal label. And this ordinal label will encode our relevance score. And so this is going to be the teaching signal that encodes the relevance label. And we're going to have kind of n many of these strings outputs, and each one might have a varying number of individual strings contained within them. Okay, great. So what data are we going to use? This has been highlighted a lot in this conference. This has been kind of very, very helpful work put out by Elastic or Endgame. And so, these guys open sourced a set of malware features and identifiable binaries. So you can see the work at the archive paper or their GitHub. But it's over 1 million PE files and split up into testing and training sets, and also malicious and benign. And they define malicious as anything that's more than 40 VirusTotal vendors is saying malicious. So this is kind of like a safe set of malware for us to work with in that sense. It's something that a lot of vendors are agreeing upon. So what we did is we ran strings on those binaries, and we output over 3 billion ASCII and Unicode strings, so we generated a ton of strings on disk. So we don't need to train on all of those, right? We sample that down to about 40,000 samples, or about 30 million strings. And then kind of the crux here is we want to label these strings. EMBER doesn't have strings that have labels with them, so we tackle this using weak supervision. And so this has been kind of discussed a little bit here in the con so far, but people are tackling this in different ways. Cybersecurity data is slightly different than your normal kind of images, right? You can't just shove the data to Mechanical Turk and have someone say, there is a cat here, or this text contains violence, right? So you kind of require some more domain experience. It's more like medical imaging data, like radiology data, than it is like simple tasks like there's a dog in this photo, for example. So there's a fundamental data labeling bottleneck when it comes to cybersecurity data, and people deal with this in many different ways. You've heard some different techniques like relying on crowdsourced virus total labels. You've heard people using transfer learning. So you have like a further ahead starting point that you can then use to fine tune on your problem. So these are really, really creative approaches. We're going to go with the weak supervision approach. And so what we want to do is create a bunch of labeling functions on our data and generate weak labels for them. And so by weak, I mean they're noisy, they're not 100% accurate, and we're going to frame this according to like an ordinal task, right? So we have unlabeled data, we run a bunch of labeling functions over them, now we have labeled data, right? And so our labeled data will look like ordinal labels, and so you might not be able to see this, but each one will take as input a single string, and will output, here it's kind of encoded as a very relevant, irrelevant, semi-relevant score, but it'll output a score, and the score will range from 0 to 7, 0 to 6, 7 total choices, and if a string is not labeled by a labeling function, it will be like an abstain, there will be like no vote, and what we do here in the learning to rank framework is we actually take those ones that aren't voted on and apply the neutral label to them, so they end up more in the middle of these things, right? So they're not irrelevant, they're not relevant, they're somewhere in between in this nebulous world, and we can use that to get feedback and iterate. And so what do we use for labeling functions themselves? We can get creative here, do more NLP type stuff, so you can look at things like entropy of the string itself, which is kind of a measure of its chaos or randomness. So things with low entropy, like on the left, repeating Qs, repeating Ps, repeating Ws. Those are very regular strings in terms of their character frequencies, and they also have very low entropy, and those we don't really care about. Same thing with high entropy strings. These are essentially enumerations of the entire list of the strings in our set, and so these are very chaotic, these are very irregular, and so what we want to focus on here is neither of those things. Both of those things don't matter for malware analysis, so we have like a Goldilocks zone here right in the middle. That are interesting. We can build a labeling function to reflect that. Now again, we can do more of that was like a memory list model. We could do more of like a memory-based model or like a single step transition-based model here using Markov modeling. And here, we can take an interesting set of strings that we know are relevant for malware, and we can train a Markov model over it, and we can build out transition probabilities between characters within that set. And you'll see, if character transitions occur frequently, that will be reflected by higher relative scores. So T back to itself might be 0.14 because HTTP occurs frequently within relevant malware strings, for example. And then we can build out some kind of threshold here that should hopefully, at least in a noisy way, separate our relevant strings for malware analysis from our irrelevant ones. So again, this can be like another labeling function that we apply. And here's what that looks like. So the ones on the right-hand side that have high average transition probabilities for the entire character sequence are going to be potentially relevant for us, and the ones that have low transition probabilities on average are going to be potentially irrelevant for us. So we can build that out. You can also do regexes, so these don't have to be as complex as that. They can be very simple. Regexes, does this look like a host or a network indicator? They could be more like base64 type of things, format specifiers. The point being that we're having reverse engineers write a lot of these regex functions. So we're having them input this data and this knowledge directly into the model. And so how does this work in practice? We use a tool called Snorkel. It's a utility. The underlying problem of this approach is that when you generate a bunch of labeling functions that are weakly supervised, they're going to have different accuracies between them. They're going to have different correlations between them, so they're going to disagree sometimes with each other. You can imagine that an NLP-based one using entropy is going to disagree a lot with some more interesting strings, right? And they're going to have different certainties. And so we can model this in a generative way, and this is kind of how Snorkel is built. Snorkel is a nice scikit-learn open source machine learning package that I highly recommend you check out. They solve this problem of generating probabilistic labels using the inverse generalized covariance matrix of these labeling functions. They take that matrix and they take the covariance matrix of it and they perform robust PCA on that. And they're able to kind of segment out or decompose the signal from that noise. And basically what this does is generate probabilistic labels or a distribution of labels for each of the strings from your model. And so they recently published a paper that you should check out if you want more details on that. And so what models do we use for this now? We're going to use learning to rank models. One of them is a gradient boosted decision tree. So people should know what this is by now, but just individual decision trees that are weighted and composed as an ensemble. We use late GBM for our approach. And we used a learning to rank objective function for this. And we also use neural networks. So I'd point people to TF ranking, which is another open source tool that allows you to compose neural network based learning to rank objective functions in like a very easy and modular way. Right? So we have different kind of competing models that we're going to use for this task. And we're going to evaluate it using the normalized discounted cumulative gain. And so here's the summary of what we're doing. We have an input query of strings. We're going to predict it from our trained model that we've trained using our labeling functions, the labels generated from that. And we're going to generate a prediction, and so each string will be associated with a specific score. And those scores are what's output by the model, and we're going to end up sorting the output by those scores, and voila, you have lists of strings that are ranked according to their relevance for malware analysis. So that works fine, but we want to convince ourselves that this works for many samples and not just a single one. And so to do that, you can calculate a score for each one and compute like a metric over all these things. And we use NDCG, normalized discounted cumulative gain. It sounds complex. It's not. I won't show the math, but you start with the gain, which is the magnitude of each of these scores. You add them up for the entire sample. So each string within a given string's output, you'll add up the scores. You'll discount them by some monotonically increasing function like a logarithm, and this will make sure that the ones that are ranked towards the top are paid attention to more by our algorithm than the ones towards the bottom, because those are the things that people look at more and they care more about. And then finally, we're going to normalize this because each string's output will have a different number of strings within their outputs, so you want to make sure that this can be consistent across that, across your corpus of different strings outputs independent of its length. And so we can run this and generate a test evaluation on strings that we haven't trained the algorithm with, neither training or validation. We've actually taken malware reports that Flare analysts or FireEye reverse engineer analysts have composed over the last 7 years, and they typically pull out one or two. No, sorry. They typically pull out in a yes or no fashion. Is this string interesting for this sample or is it not? And so we can use that as a way to evaluate our tool. And so if you just use those labels to compare against our algorithm, before we do that, we want to compare it just on the raw strings output itself. And so this is kind of expectedly bad. This is a kernel density where the lower NDCG score corresponds to a worse ranking for our model, and a higher one is going to be a better ranking. So if you just run vanilla strings on a sample and run this score, it's going to be expectedly bad and centered towards 0. And then if you kind of take the different algorithms that we've been talking about here, how we trained it, we see we can shift that distribution over to the right. That's kind of where we want to be. We want it to be towards 1 more. That means we're getting a more informative and more interesting ranking of strings. And we, like I said before, I introduced kind of 2 of these different approaches that we use for modeling. One was based on the gradient boosted decision tree, which kind of on average performs a little bit better than using that TF ranking, just like a very simple 2-layer feed-forward neural network. So to encode the strings as well, really quickly, we use TF-IDF. We've experimented with other approaches because TF-IDF has obvious issues with things like strings that, or at least character combinations that don't occur too frequently. You have this long tail problem and this proximity problem. So we've experimented with character embeddings too, and that's kind of a work in progress still. I could talk about that too after this. And so to put it all together, we have input files, we run strings over them, we generate training data using labeling functions in Snorkel, and then we build a model using those labels, and we can query that and generate predictions from that model. And these predictions should be more helpful for malware analysts than they were before. And so I have a quick demo here if I have time. I think I do. Shouldn't take too long. But we open sourced a tool. Can you guys see that? We open sourced a tool, so you can go up to GitHub and try this out for yourself. And so what I'm going to do here is just run a utility that we have called flare strings, which will take a binary and output both the ASCII and the Unicode strings in a Python, a pure Python-driven way. And the point of that is, we want to be able to run this across different OSs, Microsoft and Unix and Windows will have different arguments you have to pass to strings, but this kind of unifies it across those architectures. And so here, this is like the malware analyst workflow. We're scrolling through strings, kind of like I showed before. You see some junk, you see some garbage. This is a Zeus sample that was compiled from source. So you might see there's some API calls. You might see you might see a PDB path because we compiled it from source. And so yeah, this is, I'll see a DLL in there. But this is kind of the canonical process, what you would go through in this stage. Just kind of belaboring the point here, but you can probably see how this is super annoying, right? And so eventually there's that PDB. But eventually what we're going to do, there's some XML, is instead of just outputting the pure strings, we're going to pipe it through String Sifter. So this is kind of the tool that we're proposing here. And we're going to pipe it through String Sifter and look at the output. And so ideally, and as you can see in this demo, the juicier ones now are towards the top. You see those PDBs, you see some XMLs, you see some URLs and some potentially juicy API calls. And so just kind of like I described before, those ones you can get a very instantaneous look at and see how those are going to be a lot more useful. And so to kind of finish off here, the tool is live, like I said. We wanted to make it very easy for people, so it's super portable. You can download it, you can pip install it, and we provide command line tools and Docker tools, so you can use this today, you can use this afternoon. It's not only useful for strings, the strings program itself, but we also have it operate downstream from another open source tool called Floss, which is a FireEye built tool that will reveal some obfuscated strings that might have been either dynamically decrypted at runtime or built on the stack manually. So a lot of times malware authors will try to obfuscate their intention, and they know that strings are a signal for analysts, so they'll try to kind of play that cat and mouse game a little bit. And you can also use this for live memory dumps. I tried today to kind of convince you that weak supervision is like an interesting paradigm for cybersecurity in general, and that for labeled starved problems that we all have in this space, and that we can't easily open source because of concerns about privacy and other things like that, this is a good approach for us to take and get a first hack at a problem. And then kind of, this is open source now. The open source tool itself is just a serialized version of the model and not a way to train the model itself. So that might be something that we might investigate in the future, but we want to basically try to tune this model, make it more accurate and useful for users. And so by implementing more labeling functions and also running this on different file formats, we think we can kind of achieve that. So that's it. I think we have like 5 minutes for questions here if anyone has any.
Thank you. Yeah, great talk. This is a interesting tool for your tool belt. You addressed the stack strings question. I was going to have that, but do you see any benefit on like packed binaries or anything like that with this? That one's kind of a challenge.
No, but so yeah, maybe I should use the mic or not directly. I think sometimes in packed binaries you might have a string that shows up that will reveal what packer was used to pack it. So that could be useful as a first step. Another idea we've toyed with is you can imagine for packed binaries, the number of relevant strings is going to be very small compared to an unpacked binary. And so you could use a tool like this as a first step to, if you look at the distribution of scores that's output by this, you might expect packed binaries to have because there's so much fewer. You'd expect the distribution to be a lot more skewed compared to something that's unpacked, which will kind of have more of a uniform distribution, for example. So you can use it in that way. But no, for packed, yeah, this is kind of a and that it defeats this tool. But there's other tools in the malware analysis toolbox to get at that problem, obviously.
This is a really simple question, but does this tool tell you the ranking? I mean, it doesn't. I mean, implicitly it tells you the ranking, but does it tell you like relevance if you did what you just said, and it was all packed, and you were like?
Yeah. So it will output kind of deterministically, obviously, each string within a given binary. It'll associate its score with that string. Yep. Yeah, and there's arguments to kind of, at least in the command line version, you can set an option that will do that. Yeah, and you can set cutoffs for. I just want to see the top 10 or top 20, or set a score cutoff, for example, too. Yeah.
All right, does anybody have any other questions? I did have one question for you. Do you think that your rules, since your repositories tend to have a lot of strings, do you think those might be a good source of strings for training your classifier on?
It's a great question, and we've actually explored that too a little bit. They're a great weak labeling source. The risk is that if you open source stuff like that, you might be kind of giving away some secret sauce. But I do think that's like a great, if you have like a corpus of pre-deployed YAR rules, that's like a great source for information, especially if you can generalize those.
All right, let's go ahead and give our speaker a hand.